Hello everyone. Chapter 17 in class exercise 3, problem number 17-55. The 100 kilogram uniform crate C rests on the elevator floor where the coefficient of static friction is 0.4. Determine the largest initial angular acceleration alpha starting from rest at theta equal to 90 degrees without causing the crate to slip. No tipping occurs. So this is an elevator, which is a simple elevator mechanism which is designed to raise a crate to a certain height, let's say. Now, at the beginning, this angle theta is 0 degrees, oh sorry, it's 90 degrees, it's given, and at that time the system is at rest. That means when theta is 90 degree, omega angular velocity is 0. That is the first step, the first information that we have extracted from the problem. One thing that you need to decide is uh, what kind of rigid body motion is this? Is it the example of rigid body in translation or rotation or general plane motion? And this is the example of rigid body in curvilinear translation. This is actually it's combination of rotation for this one, but for the box and the middle link EB, this is curvilinear translation. So it translates but along the curvature. Okay. Now center of mass of the box is somewhere here. Let's call it G. If it's not readable, I can use pen and hopefully you can read it after that. Now there are set of equations depending on the type of the problem. If it is curvilinear translation, then these are the equations that are applicable. You don't have to worry about memorizing these equations because all these equations are given in the equation sheet along with the information on what type of motion these equations are applicable. Okay, so this is for curvilinear motion. Okay, you can look at the equation sheet; they are the same equations. Now we use here normal tangent coordinate system. That's why we have sum of forces in normal direction and tangential direction, and sum of moments about center of mass of the box is 0 because this box, it does not rotate, right, while it translates on its own axis. It just moves. So this G, it always remains vertical. So that's why the sum of moments about center of mass is 0. So let's indicate different forces which act on the rigid body. So one is mass, or so the weight of the box, which is 100 multiplied by 9.81. Okay. And then when this rotates clockwise, what is the direction in which the box can slip? Okay. Just think about it. So if this goes right with high speed, there are chances that box may slip in this direction. Now we do not know whether it slips or not, but that's why I just put word it. Sorry, it may slip in this direction. Next about the direction of the position of the normal force. So normal force acts from the platform, the elevator, onto the box, but the axis of normal force does not pass through the center of box. It passes through away from the center of box further left because that's the direction the box may slip. Okay, so if I consider that this is the center line of the box, then the normal force acts at some distance x away from the midpoint or the center of mass of the box towards left. Now you may wonder that why not normal force acts in the same line, along the same line as that of weight. This is true only when the box or the link does not move. So it's only true for statics that normal force coincides with the weight. But then in dynamics, this is not true. When things start slipping or tipping, then normal force moves away from the center line depending on the direction of slip. So that's why the normal force is at some distance x from the center line. Okay. Now angular acceleration of the link is alpha. So let's calculate first normal acceleration and tangential acceleration of the center of mass. Okay, sorry, we forgot to show different forces here. One of the forces, if box may slip towards left, then friction force acts towards right. So this is the direction where friction force can act. Okay, and because we are applying normal tangent coordinate system, when theta is 90 degree, I'll just draw this diagram here. When theta is 90 degree, then this is our tangential axis, this is our normal axis, and friction is parallel to tangential axis. Just remember this when time comes. We will use this information. So let's calculate AGN, that is normal component of the acceleration, which is, as per this equation, omega square r, where omega, that is angular velocity of the box, is 0, or the link EB is 0 because it's starting from this, so this is 0. Second is tangential component of the acceleration is alpha r, okay, where alpha is the angular acceleration and r is the radius of the link in this example, because see, this entire link has the same angular acceleration and the same you can say the speed, because the entire link is connected to point E. So we just apply this equation for point E. So whatever is the velocity of point E will be same as the for point B, because this link is fixed link, like it does not rotate while the system rotates. So we consider this distance as our radius, so that is 1.5 meters. So this is 1.5 times alpha, that is tangential acceleration. So now we can apply this equation. Sum of forces first in tangential direction is equal to m times ag tangential acceleration. Okay. And we consider that going right is positive as per this diagram. So this is our positive and this is our positive. So now we need to substitute what forces act along tangential direction. So there is only one force, that is friction. So Ff, that is friction force, is mass of the block, which is 100 multiplied by 1.5 multiplied by alpha. Okay. But okay, so next question is, what is normal friction force? So friction force is mu statics times normal force, that is 100 multiplied by 1.5 multiplied by alpha, and normal force is balancing the weight. So it's, now I'm substituting all the values. So coefficient of friction is 0.4 and normal force is nothing but weight, which is 100 multiplied by 9.81 is equal to 100 1.5 times alpha. When you solve this equation, you get alpha is equal to 2.62 radians per second square. That's one of the answers. However, the problem does not stop here, because it says that determine the largest initial angular acceleration. That's fine, we have calculated it, but then how do we make sure that the crate, if when time comes, like crate will slip and not tip? So we need to verify that. And how can we verify that? That's where we make use of this information. X is the information for the X in here. So let's do that part now. Okay. So for that, we need to apply these equations. Sum of moments about mass center counterclockwise is positive is equal to 0. Now this is only for the box and the link EB. So the forces which we need to consider, and we are taking the moment about the mass center of the box, which is here. So we need to consider the moment because of two forces. One is friction force about G. So friction is here and G is here. So this moment is counterclockwise and that is positive. So it's friction force multiplied by the height, which is half of the height of the box, which is 0.6 meters. And this is positive because it's counterclockwise. And then the second one is moment because of n about g, which is n multiplied by x, but then it's clockwise and it's negative. So it's minus n multiplied by x is equal to 0. We don't have to consider the moment of the weight force because that passes through g, so it does not have any moment about that point. So now in this equation, if when you substitute friction force and normal force, we can calculate x, and when you calculate x, we get the number that is x is equal to 0.24 meters. Now, as long as this value, the value of x, is within the half of the width of the box, okay, I'll just keep it here. So as long as this x is within the half of the width of the box, we can say that n normal force is contained within the box and it will not tip, but it will slip. Okay, so and this is the case because half of the width of the box, which is 0.6 by 2, so we can say that as long as x is less than 0.6 by 2, okay, crate may slip but not tip with this value of initial angular acceleration. Okay, and that is the end of solution. Chapter 17 in class exercise 4, problem number 17.7. The 100 kilogram wheel has a radius of gyration about its center O of k0 is equal to 500 millimeters. If the wheel starts from rest, determine its angular velocity in 3 seconds. So we need to decide what is the type of the problem. It is the rigid body problem, and whether it is the example of translation, rotation, or general plane motion. Now look at the example carefully. This wheel is a rigid body which is mounted on this shaft which goes through point O. So rigid body, and when the force P is applied, the wheel can have only rotation about O. Now because it is pinned at O, it does not slide when it rotates, it simply rotates about O. So this is the example of pure rotation. Okay. And then we need to use appropriate equations when it's pure rotation. So let's identify the information from the question. What we know from the question is this information is useful. It's starting from rest. That means its initial angular velocity is 0 radians per second. We know the radius of gyration, which is 500 millimeters. And then we also know mass of the wheel, which is 100 kilograms. Okay, so let's draw the free body diagram and kinetic diagram of the problem. For the free body diagram, I'll just draw in this figure itself. So different forces that act in this situation are P is applied force, then W or weight, which is 100 times 9.81 acceleration due to gravity. That's another one. But then this pin has also forces exerted by the rotation of the wheel. So reaction forces at the pin are OT tangential force and ON normal force. So these are the different forces, and that's our free body diagram. And kinetic diagram is, as a result of these forces, wheel has some moment of inertia and angular acceleration about point O. Okay, and if we apply normal tangent coordinate system, then the wheel has, at this point, let's say, it has some tangential acceleration and normal acceleration. Okay, or you can also draw this passing through the center of the wheel. But anyways, that's our kinetic diagram. So what next? How do we solve the problem? We need to calculate the what are we determining if the starting from this, determine its angular velocity. So we need to calculate omega for the wheel after 3 seconds, okay, when this force 100 newtons is applied on the wheel. So in this situation, If now we do not know this force, that is for tangential force, and we do not know this normal force, and we even, so if you apply the equation sum of forces in tangential direction, then that will help us to find this force. Sum of forces in normal direction will help us to find this force. But then none of this will give us the value of acceleration alpha. Okay, so we need to apply the third equation, that is sum of moments about O, which is the center of the wheel, and counterclockwise moment is positive, is equal to, this moment is not zero because wheel actually rotates. So when wheel rotates, it has some moment of inertia about O and some angular acceleration alpha. So we need to apply this equation. Sum of moments about O from this diagram is equal to I0 alpha from kinetic diagram. So I always keep on saying that for this equations of motion, for the left hand side, look into the free body diagram, and for right hand side, check the kinetic diagram. Okay. So let's call this equation 1. Now, do we know the value of I0, mass moment of inertia about O? We do not know, but we know the radius of gyration, so we can calculate it. So I0 is equal to m k0 square. This is the equation of moment of inertia, mass moment of inertia from radius of gyration. So when substitute m is equal to 100, k is equal to 0.5 square, because this 500 is millimeters. So this number is 25 kilogram meter square. Okay. Now we can substitute that in equation 1. So I'll just write it here. So equation 1 is sum of moments about O. What forces do we need to consider for the moments about O? What about the moment because of weight, tangential force, reaction force from the pin, and normal reaction force from the pin? They are zero because they all pass through O, so none of them results in any moment. The only force which we need to consider is this 100 newtons. Okay, so 100 newtons about O, and this is clockwise. When you pull this force, this moment is clockwise on the wheel, so it's negative. So it's minus 100 into 0.6, the distance between point O and the line of action of P, which is nothing but the radius of the wheel, that is 0.6 meters, equal to I0 alpha, which we already have calculated is 25 alpha. Now for alpha, we need to substitute appropriate direction, positive or negative, in this example. So this term is negative because it's again clockwise acceleration. Okay, so anything clockwise is negative for us and counterclockwise is positive. So this negative sign will get cancelled, so we can get alpha from this equation, which is 2.4 radians per second square. This is our acceleration. For our final answer, we need to calculate angular velocity omega. Now if you look at the acceleration is not function of time, it is constant. And when acceleration is constant, because alpha is constant, we can apply this equation omega equal to omega 0 plus alpha times t. So initial angular velocity is 0, angular acceleration is 2.4, and time is 3 seconds. See here, we are calculating it for 3 seconds. So then our final answer is 7.2 radians per second. And what is the direction? It's clockwise. Okay, so that's our omega. So this is the vector representation, that it has both the magnitude and direction. So always put the direction in bracket, or you can write using vector notation that omega is minus 7.2 radians per second. Sorry, I need to put the unit vector first. So this is k is unit vector and the unit is radians per second. Okay, and I have replaced this clockwise arrow with minus k in the equation. Okay. So yeah, that's our final answer. either of this answer is correct. Like you can write it this way or the other way. Okay, problem number 17.10. At the instant zone, means in this particular situation, the 30 kilogram disk has a counterclockwise angular velocity of 10 radians per second. Determine the tangential and normal components of reaction of the pin O on the disk and the angular acceleration of the disk at this instant. Okay. So this is an example of a rigid body in pure rotation, because the disk rotates with respect to O. It has just rotation, no translation. So this is pure rotation. Okay, so let me put it here. So this is again pure rotation of rigid body. These are the set of equations for pure rotation of rigid body. That is, sum of forces in normal direction is m omega square rg. Sum of forces in tangential direction is m alpha rg. Sum of moments about O is I0 alpha. And the moment of inertia of circular disk about its center of mass g is 1/2 m r square. Okay, so we need these equations. That's why I have written them here. So let's begin solving the problem. So first step is we need to define whether we are using normal tangent or xy coordinate system. So in this example, we'll use normal tangent coordinate system. So I'll just put it here. So we use normal tangent coordinates. And then the next step is we need to draw a free body diagram and corresponding kinetic diagram. Okay. So at the given instant, okay, first of all, center of mass of the disk is here. Okay. So this is center of mass of the disk G. Now this is the direction of rotation. So the center of mass goes through circular path. Okay. And at the given instant, this is the direction of tangential axis and this is the direction of normal axis. Weight of the disk acts through G, so which is straight down, which is 30 times 9.81. Okay. This force is applied at the point on the disk, but this is at an angle, so I would like to resolve these forces into along tangential and normal direction. So tangential force is horizontal component of the force, which is 4 divided by phi. This 4 divided by phi multiplied by 50, and vertical component of the force is 3 divided by phi multiplied by 50. And then we also need to consider the reaction forces at pin O. So let's call this is the tangential component of the reaction at O, and this is ON, which is the normal component of the reaction force at O. Okay. And that's our free body diagram. And our kinetic diagram, I'm drawing it here, is as a result of this forces, the center of mass has some tangential accelerations. So this is m force in the tangential force due to tangential acceleration. So mass multiplied by acceleration is force. And then its resultant force in normal direction is m agn. Okay, and this is our point of rotation, point O. And then this disk has rotation about O, so it has some moment of inertia, mass moment of inertia about O, which is I0 alpha. And this is our kinetic diagram. Okay. One thing to remember here is the distance between the point O and center of mass of the disk is called d, which is this distance. So now identify our unknown. So we are following the steps that we have discussed in this slide. So first step is you define, you select the appropriate inertial reference frame. So we are using normal tangent. Second, draw free body diagram, identify all the forces. We have done that. Draw kinetic diagram, indicate resultant forces and acceleration and moment of inertia. So we have done that as well. Next, write down the equations of motion. We already have written it. And now identify unknowns. What are our unknowns? So read the question one more time. So determine the tangential and normal components of the reaction forces at pin O. That means OT and ON, and the angular acceleration of the disk, which is alpha. So our unknowns are OT, ON, and alpha. Okay, these are our unknowns. So we have three unknowns, and the good thing is we have three equations. So each equation will give us one of the unknowns. So when we apply this equation, that's the sum of forces in normal direction, that will give us the value of ON. Sum of forces in tangential direction will give us value of OT, and third one, sum of the moments about point O will give us the value of angular acceleration alpha. However, if you carefully notice, then for the equation of tangential forces, we need the value of angular acceleration alpha. So it's a better way to start with this as the first equation. Then we get the alpha and we can use it in the tangential force equation. Okay, so that's the approach that we follow here. So let me adjust the page. Okay, hopefully you can see the figure now. Okay. Now let's apply this equation first. Sum of moments about O counterclockwise is positive is equal to I0 alpha. Now what is the value of I0? Now we know the equation for moment of inertia when the disk is rotated with respect to its mass center, but this time it's not rotated from here, it's rotated from O. So let's call this equation 1. So we need to apply the parallel axis theorem. So sum of moments about O is sum of moments about G plus mass of the disk multiplied by square of the distance between the 2 points, that is the actual point of rotation and center of mass, and that is distance d. Okay, so now let's substitute all the values. So Ig is 1/2 mr square, where r is the radius of the disk, md square, where d and r are same in this example. So when you substitute all this value, you get mi0 is equal to 4.05 kg meter square. Substitute this in equation 1. So let me do this here. So substitute this in equation 1. So sum of moments about O. So what forces, now for left hand side of the equation, refer to the free body diagram. How many forces we need to consider while we calculate moment about point O? First of all, we don't have to worry about OT and ON because they pass through O. We don't have to worry about weight because its line of action passes through that. We need to consider only components of the force which is applied on the disk, this applied force P. We just need to consider two components of that force. So it's this component, moment of this force about point O. So if you extend the line of action of this force, it's this force multiplied by this distance, which is the radius of the disk, and this force results in counterclockwise moment about O. You can visualize it that if you just pull this arrow, it tries to rotate the disk counterclockwise. Okay, and this component also results in counterclockwise moment about O, and the distance between this force and the center of rotation is also radius of the disk. So both the moments are counterclockwise. So we can apply this equation now. So sum of moments about O is I0 alpha. Counterclockwise is positive. So it's 4/5 multiplied by 50. That's just the force multiplied by radius of the disk, which is 0.3 meters, plus vertical component of the force is 3/5 multiplied by 50 multiplied by 0.3. So both these terms are just for sigma mo is equal to I0 alpha, which is 4.05 multiplied by alpha. So when you solve this equation, we get the angular acceleration of 5.185 radian per second square. Okay, that's our one of the unknowns. Okay, we can actually put the direction as well, that it's counterclockwise. Okay. That's one solution from one equation. I have to frequently adjust the paper because the document camera which I use does not feed to the entire paper, like does not see the entire paper all at once. Okay, so now the next one is, let's apply the equation sum of forces in normal direction going up is positive for normal is equal to m omega square rg. So how many forces we need to consider it for normal direction? So one of the force is normal component of the reaction which goes up, then weight which goes down, so it's negative, and the vertical component of the force. Yeah, do not forget this force. Okay, this is the vertical component of the applied force. Oftentimes student forget counting this in the equation and they end up getting wrong answers. Is equal to mass of the disk, so m, omega angular velocity of the disk, it's given in the problem, that is 10 radians per second square, and r is the radius of the disk, which is 0.3 meters. So everything is known in this equation except on. So on is 1.16 kilonewtons, and the direction is it's going up. Okay, so that's our second unknown. And the last one is we need to apply sum of forces in tangential direction going right is positive is equal to m alpha rg. Okay, so you substitute all the left hand side of the equation from the free body diagram, consider only the forces along the tangential direction. So one of them is reaction at the pin, plus there is only other second force is the tangential component of the applied force is equal to 30 multiplied by acceleration 5.185. See, this is the same acceleration that we have calculated. That's why I told you to solve this equation first. Otherwise, you can't have this. You can't proceed further because if you don't know angular acceleration. Multiplied by radius of the disk is 0.3. You solve this equation, you get OT is equal to 6.67 newtons, and it's going right. And that's our third unknown. Okay, so we have solved for all three unknowns, that is normal component of the reaction, tangential component of the reaction, and the angular acceleration of the disk. Okay, so that's the end of solution. This is our last problem from chapter 17, problem number 17.14. The 100 kilogram cylinder rolls without slipping on the horizontal plane. Determine the acceleration of its mass center and its angular acceleration. So this is the example of wheel rolls without slipping. If you consider the wheel as a rigid body, then it not only rotates about its center, but it also translates. So this is also the case of general plane motion. Okay, so let me write it here. So that's general plane motion. And these are the equations for general plane motion, where we use xy coordinate system. So I have defined xy here, where x positive is going right, y positive is going up. Sum of forces in x direction is mass time x component of the acceleration of center of mass, and then y component of the acceleration of center of mass. Sum of moments about point A, we call this point which is in contact with the ground as point A, so is equal to kinetic moment about that point. And since it rolls without sleeping, we can also say that acceleration of center of mass of the wheel. By the way, where is the center of mass? It's here. That's g, is equal to angular acceleration multiplied by radius of the wheel, which is 0.3. Okay, and when this pulls here, the direction of the angular acceleration is clockwise. Okay, so that's alpha. And we also need this information that moment of inertia of disk about its center of mass is 1/2 mr square. Now let's draw the free body diagram. So for that we need to consider the various forces acting on the disk. So one of them is weight, which is here, so this is W. Then normal force at A, so this is normal force. Then friction force. What is the direction of friction force? So when this goes right, so friction acts left, so this is friction force FF. And then applied force. Yeah, that's it. So we have four forces, W, N, F, and P, and that's our that's our free body diagram, FBD. And our kinetic diagram, you should draw this on the side. I'm just drawing it here. As a result of this forces, center of mass of the disk has acceleration AgX, so x component of the acceleration, and because of the rotation and moment of inertia, it has angular acceleration, angular moment, which is I0 alpha. Okay, so this is resultant force and this is resultant the resultant moment because of all the forces. Okay. And this one is our kinetic diagram. So what equation can we apply to this problem? So the best equation we can apply right now is we can calculate the moment about O. Now we just need to calculate, okay, by the way, identify our unknowns. So what are our unknowns? We need to calculate the acceleration of center of mass of the disk. That is, this is our first unknown, and the angular acceleration, this is our second unknown. So we have two unknowns in this problem, and the unknowns are alpha and AgX. Okay, so let's write the equation. Okay, let's write this equation. Sum of moments about A is equal to kinetic moments about A. So for left hand side of the equation, we need to refer to this diagram. So what forces we need to consider while calculating moment about A? So we don't have to consider friction and normal force because they both pass through A. We don't have to worry about W as well because the line of action of W passes through A, so that is also 0. Only force we need to consider about is this 200 newtons and its moment about A. And this force moment about point A is clockwise, right? So it's negative. So 200 multiplied by 0.3, that's negative, equal to kinetic moment about A. For that we need to refer to the kinetic diagram. So the moment of this force, so this is the force and its moment about A is this force multiplied by this radius, so that's clockwise moment. And then we also need to consider the moment of, because of the moment of inertia and angular acceleration, so I0 alpha, and that is also clockwise, so it is negative. Okay, so let's write this equation. Sum of moments about A is equal to sum of all kinetic moments about A. So this is minus 208 into 0.3 from free body diagram, and this is minus m AgX minus Ig alpha. Let's call this equation number 1. Now in this equation we have our both the unknowns, that is AgX and alpha, but now we cannot solve one equation with two unknowns, so we need second equation, and our second equation is this, which is agx is equal to alpha r. So that's our second equation. So, and we need to calculate moment of inertia ig as well. So ig is 1/2 mr square for the disk. So after you substitute the number, so this is 100.3 square, we get this as 4.5 kg meter square. That's our moment of inertia about its mass center. Okay. And that's number 3. So now it's time to substitute 2 and 3 into equation 1. So 2 and 3 in equation 1, when we do that, we'll get it as minus 200.3 is equal to minus 100. Agx is now r alpha, so it's alpha multiplied by 0.3 and minus, this is 4.5 multiplied by alpha. So is that correct? Let me just double check. So this is m, ag is r alpha, so r alpha, yeah, that's fine. And now from this equation, when we solve it, we will get alpha is equal to 4.44 radians per second squared, because this is the acceleration and it's clockwise. Okay, and then from alpha, when you substitute alpha in equation 2 and multiply that with r, we'll get our second unknown, which is agx, that is the acceleration of mass center of the wheel, and that is 1.33, and the unit is, this is linear acceleration, so it's meter per second square, it's going right. So we have our two unknowns, we have solved for it.